All right, so today we're going to be having our final exam review. So I'm just going to talk a little bit about the final, what you can expect, and then we're just going to do some problems that are final type problems. So the first thing is that the exam, as I mentioned, will cover chapters 27, 28, and 29, or we'll focus on those chapters, I should say. So again, as you've seen and as I've mentioned before, there are some problems in chapters 27, 28, and 29 that you can't really solve without some of our previous material. So we still see Coulomb's law in some problems where you have to find like the total force. We still see Ohm's law when we find the induced current. We still use a little bit of capacitors for, the changing electric field produces a magnetic field. We use the capacitor for that. Conservation of energy, we're going to do a problem today that involves conservation of energy. So some of those things you can't really forget for the final. You still need them in chapters 27, 28, and 29, but there is material that is no longer relevant for these topics. So like discharging and charging a capacitor from chapter 26, you don't need. Dielectrics, you don't need. Things like that, that haven't popped up again, you don't need. And I also won't I won't be asking any questions that are like specifically and only about earlier material. So there won't be a question where the entire question is just like calculate the potential of this charge distribution. It will be a conservation of energy problem that's worked into a magnetism problem, as you'll see today. So, okay, so that's like the cumulativeness of the exam. So it will be set up similar to the practice final. There's a practice final under quizzes. The solutions are there. Again, I highly recommend that you wait until like Saturday or Sunday to take the practice final under exam conditions. So time yourself, don't have any notes besides the formula sheet and see how you do. Because if you sort of just go through the practice final with the solutions in front of you, you're not really getting any benefit from it. And you're not really gauging what topics you still need to study, or do you need to speed up your test taking. So I would highly recommend only doing the practice final under exam conditions. And also, as I've mentioned before, the good thing about EM is that it gets complicated really fast. So there's only so many types of questions that you can expect to see on the exam that are like reasonable to solve in the amount of time that you have. So if you do a lot of problems, if you do all of the lecture problems, the discussion problems, the homework problems, you'll see that they all kind of fit into like just a couple of different type of problem. So if you practice a lot and do a lot of problems, you'll see that we're sort of just repeating the same problems over and over again with just different numbers or slightly different setup. So it's good in that sense, because if you just do a lot of problems, you basically have seen everything that could possibly be on the final. So everything that we cover in lecture and discussion and homework is everything that you could possibly see. I'm not going to like surprise you with some new concepts and new topics on the final exam. So if you just spend a lot of time problem solving and do a lot of problems, you've really seen everything that could possibly be on the final exam. So there's only a few types of problems. And you want to aim for the second you read a problem, you immediately know what type of problem it is and what sort of problem-solving technique you need to solve that problem. And that only comes with a lot of practice. The other thing is you want to spend like 90% of your time actually doing problems. So 90% of study time should be problem-solving. So I know for probably a lot of your classes, especially if you're taking like a lot of gen ed classes, the bulk of your like study time is going to be reading, the material. And you sort of get used to this, like reading the textbook or reading the material is how you study. But in physics and math, that's really, it can be very counterproductive. You really don't want to spend the bulk of your time reading the textbook. You want to spend the bulk of your time problem solving. You want to be actively solving problems. So, spend most of your time solving problems. Obviously check the textbook and, read over the relevant sections and stuff, or if you're not understanding something, obviously read it. But most of your time you want to be solving problems. Don't have your textbook open for 4 hours and sort of think that that's effective studying, because it's really not. You really need to be problem solving actively. And sort of a corollary to that is that you want to actually, you want to make sure that you can reproduce solutions. So when you're either going over lecture problems or going over the practice final when you're done, make sure that you can reproduce solutions. And I say that because it's very easy when you have solutions in front of you, whether it's the homework or the lecture or the practice final. When you have solutions in front of you, it's very easy to look at it and be like, okay, yeah, I understand all these steps. And then when the exam comes and now you're under time pressure, you're nervous, you sort of completely forget the solution. And without that prompt there, that like solution telling you what step to take next or where to start, you realize you can't actually reproduce the solution. So make sure that you can write out the solution yourself without taking any hints from like a solution manual or the answers, because obviously that's what you're going to have to do on the final exam. And the other thing is that the final exam review from summer session 1 is available as well. So the summer session 1 review is available. So that's listed on the, if you go to the lecture page at the bottom, I have a link for the summer session 1 final review. So that's available to you. I highly recommend going through that as well, because I just go through different problems. So the problems I go through today are going to be different than the problems that I went through in summer session 1. And I highly recommend that you watch it as well. All of the problems in that review focus on the right-hand rule. So, all right, so let's get started with today's review. So the first thing I'm gonna do is the right-hand rule. So let's focus on that first. Okay, so this is just a diagram that I took out of the Halliday-Resnick book, which again is a really good book, and I have a link for it in the lecture page as well at the top. So the first thing is our right-hand rule with Cartesian coordinates. So Cartesian coordinates are just like x hat, y hat, z hat. So this is the right-hand rule for Cartesian coordinates. So some of the formulas we've seen that use the Cartesian right-hand rule are our Lorentz force law, obviously. So we have Q V cross B gave us the force on a charged particle from an external magnetic field. What else? We had the magnetic field of a charged particle. And we had the mu naught over 4 pi. So that used the Cartesian right-hand rule. The Biot-Savart law used the Cartesian right-hand rule. And so for this, what you want to do is you put your hand in the direction of the first vector. So remember, always use your right hand. So you put your hand in the direction of the first vector. So let's say my first vector, my velocity, let's say, is going into my page here. So I put my hand in the direction of the first vector. So we'll call that, so the first vector, put your hand in that direction, and then you bend your fingers in the direction of the second vector. So like if I have my hand like this, I just bend my fingers at a 90-degree angle, right? Because it's Cartesian, so all of the vectors are at 90 degrees to each other. They're perpendicular. So I just have my hand in the direction of my first vector, which in the case of the Lorentz force law is just my velocity. I bend my fingers 90 degrees in the direction of the magnetic field. If my magnetic field is pointing downward, my fingers bend down. Now, if my magnetic field was pointing up, in order to bend my fingers at a 90-degree angle up, I would obviously have to turn my hand over, bend them at a 90-degree angle, and then your thumb is pointing in the direction of that third vector. So the second vector, bend fingers at a 90-degree angle from your hand, and then your resultant vector is your thumb. So in the first case where I had my velocity going this way, and then my fingers bent down 90 degrees, my thumb is now into the page. In the other case, if my magnetic field was pointing upward, I put my hands like this, I bend my fingers 90 degrees, and then my thumb is now pointing away from me or out of the page. And now remember that if we have so this is for a positive particle. So remember that if we have a negative particle, so if we're doing the Lorentz force law for a negative particle, we have a negative sign out here. So let's say you do your right hand rule and the velocity is this way, the magnetic field is this way, and then your thumb is pointing backwards out of the page. If you have an electron that you're looking at, you would then have to flip the direction, and then your thumb would be pointing into the page because of this extra negative sign here from the charge of the electron. And the same thing goes for here. If you're calculating the magnetic field of an electron, you do your right hand rule as if it's a positive particle, and then whatever resultant direction you get at the end, you just flip that because you have a negative sign out in front. Okay, and then remember for our cross product, we can write this little circle. We have like I hat, J hat, K hat, or X hat, Y hat, Z hat, whatever you prefer. You draw your little circle here, and going clockwise gives you your cross product. So like I hat cross J hat is K hat. So we go clockwise around our circle. J hat cross K hat is I hat. K hat cross I hat is J hat. And then if you go backwards around your circle, you introduce a negative sign. So if you do like I hat cross K hat, if you're going counterclockwise, so like I hat cross K hat will give you a negative J hat. K hat cross J hat will give you a negative I hat. So you just introduce a negative sign if you go counterclockwise around your circle. Likewise, if let's say you have like negative or I hat cross negative J hat, let's say. What is that? Well, you have I hat cross negative J hat, so you can just sort of factor out your negative sign. So just factor out your negative sign and just put your negative sign out there. And then say, okay, I hat cross J hat is what? Well, I hat cross J hat is K hat. And then just add your negative sign back. So then you have a negative K hat there. So you can factor negative signs out just like you would in normal multiplication. Similarly, if instead, let's say I had negative I hat cross negative J hat, my negative signs just cancel out and I'm just left with K hat. So this is just equal to like I hat. This would be the same as I hat cross J hat is equal to positive K hat. Okay, and then the other really important thing is to make sure that you remember that the cross product is not commutative. So you cannot do A hat cross B hat is not the same as B hat cross A hat. These differ by a negative sign, so you have to be really, really careful when you're doing your right-hand rule with either the Lorentz force law or you're finding the magnetic field of a point particle. You have to be really, really careful that you cross the vectors in the correct order. So for the Lorentz force law, your hand is always the direction of the velocity because it's always the first vector. This is Lorentz force law. It has to be V cross B. It will never be B cross V. So you have to do your velocity first. So your hand will always be the direction of the velocity. Your bent fingers will always be the direction of the external magnetic field, and your thumb will always be the resultant vector. So there were some questions where it said, I think for homework, you did some questions where it's like, this is the velocity, this is the resultant force, what's the magnetic field? So there, you have to be careful because, so let's say we have F equals QV cross B. And let's say the problem says, okay, the velocity, it's a proton, so, this is positive. The velocity is in the I hat direction, let's say. So if the velocity is in the I hat direction and the force is in the K hat direction, what direction is the magnetic field in? So for that one, you would have to say, okay, I crossed into what vector will give me K hat? I saw a lot of people, and also last summer session, this is like a very common mistake. you see two vectors and you just immediately take the cross product of them, and then you end up with the wrong answer. So you have to do it in the right order. So you have to say I hat crossed into what is equal to k hat. You can't just immediately go I hat cross k hat, because those are my two vectors. So I hat crossed into what vector will give me k hat? Well, I can just look at my little circle right here and say, okay, I hat crossed into j hat will give me k hat. So my magnetic field has to be j hat. Or let's say there was a negative sign, make it a little bit more difficult. Let's say my velocity was in the j hat direction and my force was in the k hat direction. Then I would have to say, all right, j hat cross what is equal to k hat? Well, j hat crossed, I have to go backwards now, right? I have to go counterclockwise. J hat crossed into I hat will give me negative k hat. So I'm looking for positive k hat. So that means that I need another negative sign. So j hat crossed into negative I hat will give me positive k hat. So you have to be very careful with these things. So this was negative I hat. And we can check this by saying, okay, j hat crossed into negative I hat. I can factor out my negative sign, right? So I can do j hat crossed into I hat. Let me draw this here. So j hat crossed into I hat gives me negative k hat. So this here is negative k hat. So then that means I have a negative k hat, which gives me positive k hat, which is what I was looking for. So you have to be really, really careful with these cross product. Make sure you're going in the right order, and be really careful of your negative signs, because obviously negative signs are very tricky. So now let's say we had some problem where we're doing the Lorentz force law again. And let's say that in the problem our velocity is like in the x hat and y hat direction. And our magnetic field was in, let's say, just the x hat. So when I go to take the cross product of these two, I immediately know that the x component of my velocity is not going to contribute to the magnetic force because it's in the same direction as the magnetic field. So remember, two vectors that are parallel have a cross product of 0. So like x crossed into x is 0, y crossed into y is 0, z hat or k hat, whatever. Z hat crossed into z hat is 0. So any parallel vectors, the cross product of parallel vectors is always 0. The definition of cross product is that it takes two perpendicular vectors and returns a third mutually perpendicular vector. So the way the cross product is defined is that V, B, and F all have to be perpendicular. No two of them can be parallel because then the cross product would just be 0. So by definition, if you have a magnetic force, that means that your velocity and your magnetic field must have some perpendicular component because if they were parallel, the force would just be 0. So a quick way to do like a cross product like this, now you could go through the whole cross product where you write the little box and you do the whole thing out, but that's a little bit more complicated than you need to for this class. So you can just look at this right away and say, okay, if I do V cross B, I have Vx plus Vy crossed into Bx. And I know right away that since it's a cross product, the x hat components don't contribute to my force, and only the y hat crossed x hat components will contribute to my force. So then I can just say, okay, the x hat component doesn't matter because my B is in the x hat direction. And so then I can just say, all right, my cross product then is just Vy in the y hat crossed into Bx in the x hat. So I have Vy times Bx, and then I have y hat cross x hat, and then we can just look at our little circle here and say, okay, y hat crossed into x hat is negative k hat or negative z hat. So this would just be negative z hat, and then your answer would just be, you know, vy times bx negative z hat. So for these types of problems, so there was question 5 on your practice final. So question 5 on the practice final. So that one had like a proton and an electron. You have to find, you know, like the magnetic force that one exerts on the other, the total force between them, and that was also very similar to a homework problem that you had. So question 5 on the practice final, I go over that in the summer session 1 final review. So if you want to see like a verbal explanation of that, that's in the summer session 1 final review, which, as I mentioned, is linked on the lecture page with all the other videos. Okay, so now let's do, let's look at the right-hand rule for like our cylindrical setups. So let's do cylindrical right-hand rule. So the cylindrical right-hand rule is much easier than the Cartesian one because there's really only 2 directions that we have to worry about. So you really just have to worry about your thumb and your fingers. So the cylindrical, your thumb, and then your curled fingers. So the thumb, if you've taken like vector calculus or something, and you're familiar with cylindrical coordinates, if not, that's okay, don't worry. Your thumb corresponds to the z hat direction, and your curled fingers correspond to the phi hat direction. So the right-hand rule in cylindrical coordinates is much easier than you probably think it is because, like I said, there's only 2 things to worry about. There's a straight thing and then there's a curling thing. So we've seen, in the case of cylindrical coordinates, we've seen straight wires. So those would correspond to your thumb. If you have like a infinite wire traveling in some direction or, you know, oriented in some direction, that wire corresponds to your thumb. So let's say, you know, if this is my wire, and the current is going this way, I would just point my thumb in the direction of the current, and then my hands curl in the direction of the magnetic field. So it's important to note here that unlike the Cartesian right-hand rule, my hands here are curled because remember, the magnetic field curls around the wire. So I no longer have these like 90-degree like straight fingers. I have a curling, you know, it's curling and rotating around that straight thing, which is my thumb. So we have straight wires and then a curling magnetic field. So the straight wire is your thumb, and the curling magnetic field is your fingers. That works whatever direction your current is in, just point your thumb in that direction. Your hands naturally curl in the direction of the magnetic field produced by that current. If you have a curling current, so if you have a curling current, so let's say like in a solenoid, where in a solenoid your current is going in a circle, right? It's wound around the turns of those coils. Then you just curl your hands in the direction of the thing that is curling, which is the current, and your thumb points in the direction of the magnetic field. So if you have a curling current, you get a straight magnetic field, like in a solenoid. So here, your curling current is your curled fingers, obviously. And then the straight thing is your straight finger, which is your thumb. And so this works the other way as well. So like when we do like Lenz's law or Faraday's law, when we have an induced magnetic flux, you say, okay, I want my magnetic flux, my induced magnetic flux to, let's say, be into the page. So you point your thumb into the page, and then your hand naturally curls in the direction of the current that would be required to create a magnetic field in that direction. So I know it sounds like stupid, but it really is this easy. You just point your thumb in the direction of the straight thing. So whatever is in your problem, whether it's a uniform straight magnetic field or a straight current, you just point your thumb in that direction. And then your curled fingers will be whatever the curling thing is. So it really is that simple. And you only have two choices. You only have a magnetic field and a current. So one of them is your straight finger, your thumb. So depending on which one of them is straight, that one will be your thumb. And the other one will be the curling thing, and it will be in the direction of your curled fingers. But it's just important to note that this is for things that are like cylindrical in nature, so like a loop of wire with a magnetic field, a solenoid, an infinitely straight wire, because we know that the magnetic field will sort of be cylindrical around it. So don't use this if we have like Lorenz's law or something. This is only for cylindrical setups when we have like the magnetic field and a current. All right, so that covers our right-hand rule review. Now, as I said, pretty much I think all of the problems that I went over in summer session 1 final review involve the right-hand rule. So if you still want, if you want more practice with those, that'd be a really good video to watch. Okay, so now let's go on to Ampere's law. So there will absolutely be a question on Ampere's law on the final. But the good thing about Ampere's law is that there's really not that many variations of it. So as I said, in the intro, like there's really only so many types of problems that you'll like realistically see. And Ampere's law is definitely one of them. There's only so many scenarios, just like with Gauss's law, there's really not that many scenarios where the integral is easy to solve and where Ampere's law is useful. So, for a solenoid even, you don't even really have to use Ampere's law on a solenoid because it just gives you one answer, right? We saw how to derive the magnetic field for a solenoid using Ampere's law, and we just found that it was mu naught Ni. And that's really it. Like there's nothing else to do with Ampere's law on a solenoid. Same thing with a toroid. So that's for a solenoid. There's toroids only have one magnetic field, so once you see the magnetic field of one toroid, you've seen them all, you just plug in different numbers maybe. So there's really not too much to do with Ampere's law with a toroid. Once you understand just how to derive it in those two cases, every Ampere's law application for any solenoid and any toroid. And the only ones that can really sort of throw in a little bit of variety are like cylindrical wires. But even those, there's only so many different variations of like concentric cylinders that you could possibly have, especially since, we don't do any sort of like crazy cylindrical integrals really. So as we saw before, for a infinite wire, this is our magnetic field. And then the only variations you have on this are like, let's say you have a wire of some radius and it has a current I spread uniformly throughout. And we did this in lecture where we said, okay, we have this current spread uniformly on its cross section. We have to find the current density first. And then, when we do I enclosed, we do the current density times that area that is enclosed by our Amperian loop. So, any Ampere's law problem where it's a thick cylinder of some radius, you're going to solve in the exact same way as we did in lecture. And then maybe another type is, which we also did in lecture, where it was sort of like a donut shape. So we had a infinite cylinder where like the center was cut out, and we again had to find, it was still the same exact procedure though. We had to find the current density, and then when you find the enclosed current, for Ampere's law, you just multiply by the area. It's kind of the same setup. So we did both of these in lecture, so definitely go over both of these for sure. And then in discussion, you did one where it was like a thick cylinder, and then it was surrounded by like another cylinder. And then you had currents going either in the same way you had one current like coming out of the page, one current going into the page, then both coming out of the page. So there's sort of some, variations with what direction your current could go in. But really, like, this is kind of it. You can have just like concentric cylinders, and, whether you have like, one cylinder with another one outside of it, or you've got 3 cylinders or 5 cylinders, like once you understand how to apply Ampere's law to one case, you understand how to just like iterate it over, 3 different cylinders or something like that. So there's really not too many variations for Ampere's law. It's pretty much like a thin wire, a thick wire, a wire with a hole cut out in the center, those concentric cylinders, and that's really it. And we did all of those between lecture and discussion. We covered all of those variations. So if you just go over the lecture and discussion problems for Ampere's law, you're pretty much going to know all of the possible types of Ampere's law problems that you could see on the exam. Okay, so this is our first problem. So we have this is a velocity selector and a conservation of energy problem. So we have a proton is accelerated through a potential difference and enters a region with a uniform electric field, E is equal to 135 newtons per coulomb, and a uniform magnetic field of 0.02 Tesla, such that it passes through undeflected. So we have a velocity selector here. So what is the particle's velocity as it enters the velocity selector? So we're told that it passes through undeflected. So remember, for a velocity selector, so we have here, for a velocity selector, the magnetic and electric forces perfectly cancel out. So we have QVB is equal to QE in a velocity selector. You can see your Q's cancel, and if you solve for V, you just get V is equal to the electric field magnitude over the magnetic field magnitude. So part A is easy enough. We just divide the electric field by the magnetic field. So this is part A. So E was 135 and B was 0.02. So that comes out to 6,750 meters per second. All right, so that's part A. Now for part B, what is the potential difference V? So what potential difference is this proton accelerated through such that it has this velocity when it gets to the end of that potential difference? So this is going to be a conservation of energy problem. So this is our initial position. This is our final position. So it starts off at the beginning of whatever potential difference we have here. It's accelerated up to some velocity. And then it has that final velocity as it now enters the velocity selector. So we want to do conservation of energy. So we have the kinetic initial plus the potential initial is equal to the kinetic final plus the potential final. So we can assume that our initial kinetic energy is 0. Whenever it says like something is accelerated through some potential difference, you can almost always assume that the initial velocity was 0 unless it says otherwise. So we can assume our initial velocity is 0 here, and all of our energy then initially is potential. Then when it gets to the end of the potential difference here, it has all kinetic energy and no potential energy. So we have the initial potential is Q times V, and then 1/2 mv squared. Where this V, so we have 2 V's, so just be careful. This V is a capital V, it's the potential here, the potential difference, and then is the final velocity. So I should have written here, I should have delta V up here. Okay, so now I want to just solve for V, but I have everything else. I know the charge of a proton, I know the mass of a proton, and I found its velocity already in part A. So this is for a proton. So we just have that the potential is the mass of the proton, Vf squared over 2q, which is just the mass of a proton, and then E over B as we just found in part A, and then 2 times the charge. So you plug in your numbers there, and remember for the exam you'll have the mass of a proton and everything is given to you on the top. So you just plug in all your numbers there and you end up with 0.237 volts. So this region has a potential difference of 0.237 volts. Okay, and then for part C, it says if the electric field is directed downwards, so as it's drawn, the electric field is directed downwards, what direction must the magnetic field be directed? In what direction must the magnetic field be directed such that the proton passes through undeflected? So what direction is our magnetic field here? So if our electric field is directed downwards, we know that means we want our magnetic force to be directed upwards, because the electric force is going to be downwards. The magnetic force needs to counteract that and be directed upwards. So if our velocity, remember we're going to have QVB. So if our magnetic force, we know we want to be upwards, and the velocity is to the right, we put our hand in the direction of the velocity, and we want our thumb to be pointing up. So what direction does that mean our fingers have to bend in? Well, luckily that was easy. Our fingers just have to bend into the page here. So in order for our thumb to be pointing upward, if our hand starts pointing in the direction of the velocity this way, our thumb is up. If we bend our fingers into the page, so we want the magnetic field to be into the page. So the magnetic field is into the page. Okay, so that's this problem. So now let's go on to question 7 from the practice final I want to go over, since that's a good problem. All right, so this is question 7 from the practice final. So for problems like this, what I recommend doing is when you see like a lot of numbers and variables and stuff, just write everything down so that it's clear and you see like what variables you have and what variables you don't have. You know, when I was a student, if it's very hard sort of to like sometimes absorb all that information on a test when you're nervous without writing it down, and writing it down would really help me see what information I had and sort of show me where I needed to go in the problem, because it was very easy to see, oh, I don't have the EMF or something like that. So what I recommend doing is we have a large solenoid and a wire. So write down everything for the solenoid and then write down everything for the wire loop. So for an infinite solenoid, we have an infinite solenoid with a cross-sectional area of 3 centimeters squared. So the solenoid has an area, we'll call that AS, of 3 centimeters squared. Now 3 centimeters squared, I also immediately turn it into standard units. So 3 centimeters squared is 3 times 10 to the negative 4 meters. Because remember, 3 centimeters squared is 10 to the negative 4, because it's 10 to the negative 2 squared. So the area of our solenoid is 3 times 10 to the negative 4 meters squared. Okay, then we have 80 turns of wire per centimeter. So little n for this solenoid is 80 turns per centimeter. So we have 80 turns per centimeter, but we want to get it into 80 turns per meter. So we have to divide by 10 to the negative 2. So we have 80 times 100 turns per meter is our n value. Okay, then starting at t equals 0, the current is turned on and begins to increase according to this function. So our current increases according to 0.2 t squared. I'll leave out the units. And then we have a secondary wire loop of cross-sectional area 5 centimeters squared. So the area of the loop is 5 times 10 to the negative 4 meters squared. And its resistance is 2 ohms. So the resistance of this loop is 2 ohms. Okay, now I have everything, and everything's clear. And this also helps the grader, because if you have everything written out here, and let's say you accidentally didn't convert 3 centimeters squared correctly, if I see right up here that that's where you made your mistake, I'm not going to penalize you for carrying that through. Whereas if it's not really clear to me where some of the numbers came from, then I can't give you partial credit if I don't know, if I can't follow what you're doing easily. So it's always a good idea to write all this stuff out at the top. It makes it a lot easier to grade. Now we have, what is the magnitude of the magnetic field inside the solenoid as a function of time? So I asked this question, so this question was from summer session 1, and a lot of students didn't know what as a function of time means. So I'm just looking for the magnetic field as a function of t. A lot of students took the derivative of the magnetic field, or wrote out a function and solved for t. That's not what as a function of time means. It simply means you have some function and the variable is t. So that's all that means. So we want the magnetic field. We know the magnetic field of a solenoid is, for a solenoid, it's mu naught n times I. And here I is changing with time. So that's where our variable, our t, is going to come from. So we just have to plug in mu naught n it, and that's really it. So then let's just plug in, we have 0.2t here. So this is just equal to mu naught n, and then we just have 0.2t squared. So if you were to, if you were taking this exam and you left your answer like this, that's totally fine as long as your n is defined somewhere clearly. So, if you had it written out like this, where you have n is clearly equal to, 8 to the times 10 to the 4, that's fine, leaving it like this. You don't have to plug in all your numbers. It's fine to leave it like this. But you would have to have your n in standard units somewhere, because if you just said where n is 80 turns per centimeter, that wouldn't be good enough, because centimeters isn't like a standard unit. It would have to be where n is equal to, 8 times 10 to the 4 turns per meter. Okay, so this is our magnetic field as a function of time, because we have this variable t here. Now, what is the magnetic flux through the area bounded by the secondary wire loop as a function of time? So what is the magnetic flux through this area here? So for part B, we're just looking for the flux as a function of time. We know that flux is equal to B times A. So our magnetic field we have right here. So we just have mu naught n 0.2 t squared. And then our area, so the area here is technically the area of the wire loop, because it's the flux through this whole bigger loop. However, the magnetic field in this area here is 0. So the magnetic field between the wire loop and the solenoid, the magnetic field all here is 0. So that part doesn't contribute to the flux, even though it technically is included in the flux. Since you're multiplying that portion of the area by 0, where B is equal to 0, it doesn't contribute to the flux. So what you have to multiply the area here is the area of the smaller solenoid, since that's the only place where the magnetic field is non-zero. So when you actually multiply this out, you're actually going to change it into the area of the solenoid, which is 3 times 10 to the negative 4. So we have mu naught n 0.2 t squared, and then the area of the solenoid is 3 times 10 to the negative 4 meters squared. Okay, and then that is your flux as a function of time. If you simplify this a little bit, since now we kind of have a lot of numbers floating around, and you plug in 8 times 10 to the 4, multiply out the 0.2 and the 3 times 10 to the negative 4, you'll end up with mu naught times 0.48 t squared. So that's just a little bit cleaner, but either way you leave it is fine. Okay, so this is our answer. This is our flux as a function of time through that larger solenoid. And then for part C, what is the magnitude of the induced EMF in the secondary wire loop at t is equal to 2 seconds? So we need the induced EMF. So we want the EMF at t is equal to 2 seconds. So the first thing we want to do is find the EMF, obviously. So the EMF is the dt of the flux, and we already found the flux. So the flux is just this. So all we have to do is just take the derivative. So let's just take the derivative. We get mu naught times 0.48, and then the derivative just falls on that t squared part. So this is 2t. So our EMF as a function of time is just 2t. And then it says when t is equal to 2 seconds, so then we just plug in 2 seconds here, and you end up with, you multiply all that out, your mu naught, 0.48, 2 times 2, we end up with 2.41 times 10 to the negative 6 volts. So that's the EMF through that larger wire loop. And then for part D, we just want to know what is the magnitude and direction of the induced current at that same time, t is equal to 2. So we're going to use like our variation of Ohm's law. So to find the current, we have the EMF is equal to the current times the resistance. We're just looking for the current. We have the EMF and we have the resistance. So we just plug in the EMF we just found. And the resistance was 2 ohms. So we just divide that by 2. And we get 1.2 times 10 to the negative 6 amps. So that is our answer for that. And the direction, so I left out the negative signs. If you notice here when I did the EMF, I left out the negative signs because it just asked for the magnitude, so we can just ignore the negative signs. And then in part D, it asks for the direction of the current. So now I can use my right-hand rule for Lenz's law and figure out the direction of this current. So it says here, or it shows here, that my current is coming into my solenoid this way. So we can even figure out the direction of this magnetic field in here without knowing, without having it written here. So if the current is coming in this way and out this way, that means it's coming in here and then out over here, down and around. So our current is going like out of the page at the top and then into the page at the bottom. So we curl our hands in the direction of the current, and then our thumb points in the direction of the magnetic field, which we can see is in this direction, like to the right, sort of. So we have a current that's increasing in the solenoid, which means our magnetic field is increasing in the solenoid, which means the flux through this wire loop is increasing in the direction of the magnetic field. So that means that we're going to induce an EMF in the opposite direction to try to keep that flux constant. So we're going to induce, we want an induced magnetic field that's in the opposite direction. So you point your thumb in that opposite direction, so that's like to the left sort of, and we can see that our hands curl in the direction of the induced current, which is like counterclockwise now. So our induced current is counterclockwise. So the main thing that I went over this question that I want to point out is the area here. So this is important. So be really careful of problems like this. The flux through the wire loop, you really are taking the entire area of that wire loop. It's just that in this case, when we have a magnetic field going through only a portion of it, so, we have our wire loop here, so if we're looking like down on it, and then our magnetic field is only non-zero in here. So we have B is non-zero in here, and B is 0 here. When we do B dot A, so even though this area in the formula refers to the entire area of that loop, since the magnetic field is 0 all through here, it ends up not contributing. It's just this inner portion here that has a non-zero magnetic field. So that's why initially we have the area of the loop, but then when we actually plug in a value, we plug in the value only where there's a non-zero magnetic field, which is the area of the solenoid. So that's really important to understand. Make sure that, if you don't quite understand that, make sure you come to my office hours because that's a really important thing to understand. A lot of people made mistakes with that. I'd say like over half the class last summer session made that mistake. Okay, so now let's do another problem. Okay, so for this problem, we have sort of the same setup. We have an infinite solenoid with some outer loop around it. So we have an infinite solenoid with 400 turns per meter. So again, just write out everything for your solenoid and everything for your loop. So we have our infinite solenoid, N is equal to 400 turns per meter, and a cross-sectional area of 10 centimeters squared. So the area of our solenoid is 10 times 10 to the negative 4 meters squared, which is 10 to the negative 3 meters squared. And then we have the current in the solenoid decreases according to some function. So we have our current is decreasing according to this function. So this is an exponential decay. And I gave you, this is Euler's constant here, E. So I gave you Euler's constant down here, but most calculators have like a button, E to the something. So I had a couple students also who, when they saw this E, they thought that it referred to the like electron charge. So that's an understandable mistake to make, but once you do a lot of problems, you'll never see an electron charge like raised to some non-integer power, and you'll see a lot of functions where it's Euler's constant and then some function in the exponent. So, that just comes with practice, but this is Euler's constant E raised to negative 3t. So, okay, so this is our function for our current in the solenoid here. We have a second wire loop with a cross-sectional area of 100 centimeters squared. So the area of our loop is 100 centimeters squared, which is 100 times 10 to the negative 4, which is 10 to the negative 2 meters squared. And then it has a resistance of 0.05 ohms. Sorry. So we have 0.05 ohms. So now for part A, we want to know what is the magnetic field inside the solenoid at time t is equal to 0. So for part A, we need the magnetic field of a solenoid, which we know is mu naught n. In this case, our current is a function of time. So at t is equal to 0, we just plug in, we have 2 e to the negative 3 times 0. So this here is e to the 0, and anything to the 0 power is just 1. So this is just 1. So our magnetic field at t is equal to 0 is just mu naught n times 2. So n is 400, so we can rewrite this if we want. We have mu naught and then 800, and that's it. Okay, so that is our magnetic field at time t is equal to 0. This is in Tesla, obviously. Okay, and then for part B, we want to know what is the magnitude of the EMF induced in the outer loop as a function of time. So we do the same thing as we did in the previous problem. We have the EMF. I'm going to ignore the negative sign since we're looking at just the magnitude. is the time derivative of the magnetic flux through that outer loop. So that's just the magnetic field times the area of the loop. Okay, so let's figure out the flux first before we worry about the derivative. So we have the magnetic field, which we said was mu naught. Now this is a function of time, so we want to use this full equation up here. So mu naught times n times I of t, where I is that function up there. And then the area we want to plug in now is the area of the solenoid, because in this area here, even though the flux is really through the whole wire, the magnetic field is only non-zero through the solenoid. So we're going to plug in the area of the solenoid. So again, we change that area of the loop to the area of the solenoid. Okay, and then we can see that when we take the derivative, nothing's changing except our current. So this time derivative will only fall on our current here. Okay, and then this here is 2e to the negative 0.3t. So when we take that derivative, this is the only thing, obviously, that the derivative will fall on. So we have mu naught n, I'll move the area over here, and then we have 2, and then we have d dt of e to the negative 0.3 times t. So the derivative of e to the negative 3.3 times t is just negative 0.3 e to the negative 3t. So if you don't remember how to take the derivative of the exponential, so like e times x, the derivative of that is just e to the x. And then if you have like a constant in front of, let's say, your e, so if you have, for instance, d dx of e to the ax, where a is some constant, it will just be a e to the x. Okay, so that's how you take the derivative of the exponential. So we'll have mu naught n, the area of the solenoid, times 2 times negative 0.3 e to the negative 0.3 t. So again, since we're just looking at the magnitude, we can sort of just forget about this negative sign since the question only asks for the magnitude. And then if you want to simplify this a little bit and just plug in some numbers, you'll have mu naught n was 400. The area of the solenoid is 10 to the negative 3. Then we have 2, we have 0.3, and then we have e to the negative 0.3 times t. So if you simplify all of these numbers here, you end up with mu naught times 0.24 e to the negative 0.3 t, and that's your answer. So that's the EMF there. And this is in volts. Okay, so this is for part B. Now for part C, we want to know what is the current induced in the outer loop at time t is equal to 1 second. So to find, let's go on to, I guess we'll need another page. So what is the current? This is part C. We'll use the exact same Ohm's law variation that we had in the previous problem. We are looking for the current. So the current is the EMF divided by the resistance. And our EMF, we're just going to plug in this function that we found here, where t is equal to 1 second, and then divide by this resistance of 0.5 ohms. So we're going to have the EMF, the function was mu naught times 0.24 e to the negative 0.3 times 1 second for t is equal to 1, and then we had 0.05 ohms, and this gives us, so this gives us 4.4 times 10 to the negative 6 amps, so that is the magnitude of our induced current, and then that's all we needed to do for part C. So then for part D, we just want to know, is the induced current traveling in the same direction as the current in the solenoid, or in the opposite direction. So we have a decreasing current, which means a decreasing magnetic field in this solenoid. No matter what direction the current is traveling, it's decreasing, which means we have a decreasing flux, magnetic flux, going through this outer loop. So that means that, like nature, is going to want to try to keep that flux the same by creating a magnetic field to supplement that decreasing magnetic field. So the induced current will be in the same direction as the current in the infinite solenoid because it wants to try to keep that flux the same to counteract that decreasing current in the solenoid. Okay, so now let's go on to another example. All right, so for this problem, we have sort of like a mini solenoid, a mini finite solenoid within an infinitely long solenoid. So we have a long solenoid here. Whenever you see a problem that says like a long solenoid, you can just assume that means infinite. So we have a long solenoid with 220 turns per centimeter. So let's write down everything for our bigger solenoid, and then the inner coil, we'll call it. So the outer solenoid has 220 turns per centimeter. So as we saw in our other problem, that means 220 times 10 to the 2 because it's per centimeter. So this is 2.2 times 10 to the 4 turns per meter. And then it has a current at time t is equal to 0 of 1.5 amps. And we'll see that the current decreases. Its diameter is 3.2 centimeters. So I always immediately just translate this to the radius because I know you never really use diameter. So if the diameter is 3.2 centimeters, that means the radius is 1.6 centimeters, which is 0.16 meters. 0.016 meters. Okay, then we have this 130 turn closely packed coil. So for the coil, the number of turns is 130. So whenever we're doing an infinite solenoid with turns per unit length, we use lowercase n. And whenever we're talking about a total number of turns in either a toroid or a finite coil like this, we use capital N. So this coil has a diameter of 2.1 centimeters. So that means its radius is 1.05 centimeters, which means it is 0.0105 meters. Okay, the current in the solenoid is reduced to 0 at a steady rate in 25 milliseconds. So I'll say the current at time t is equal to 25 milliseconds is equal to 0 amps. All right, so the current in our outer solenoid is decreasing. What is the magnitude of the EMF that is induced in coil C while this current in the solenoid is changing? So we just need to know the EMF here, since we just want to find the magnitude. So the EMF is equal to what? So the EMF is equal to d dt of the magnetic flux, and the magnetic flux is B dot dA. So this is the area of the inner coil, that little coil there. We're looking at the flux through that inner coil, so it's the area that we plug in here is the area of that thing that we're measuring the flux through. So now we have, let's see. So now we want to find, let's find the flux here. So the flux through this coil is the magnetic field that's created by this larger solenoid. So we know that that is going to be equal to the magnetic field of a solenoid. And it has a varying current, so I'm going to leave that as a function of time so that I remember it's not a constant current. And then the area of the little coil is pi r squared, where that's the area of the coil. And then remember, I'm going to multiply my total flux by the number of turns in this coil. So I have N, because this is the flux through a single coil, or like a single turn in this larger coil. And so I multiply by N to get the total flux. So to find the total flux, I want to multiply by N. All right, so now I can find the EMF. So I know everything here. I know mu, I know N, I know the radius of the coil, I know capital N. So I just have to worry about this change in time. Now, it tells me that the current starts out at 1.5 amps, and then a very short time later, the current is 0 amps. So I can just approximate this when I take the derivative. Let me get all of my constants over on one side. So I can just approximate the derivative of the current as the change in current over the time. Since I'm looking at a very small time interval, I can just do delta I over delta t, and that's fine. So this is the 1.5 amps divided by my 25 milliseconds. So then I'm going to want to plug in all of these numbers. So I get plug in mu naught. N is 2.2 times 10 to the 4 for the solenoid, and then I have pi times the radius of my coil, which is 0.0105 squared, and then I multiply by 130 for the total number of turns in my inner coil, and then I multiply by delta I over delta t, which is 1.5 over 25 times 10 to the negative 3. And you multiply all of this out, and you get 0.075 or 75 millivolts. So this is my EMF. Okay, so this is just the magnitude of the EMF. Now, if it had asked what direction is it going in, remember when you have like little dots like this, that means that the current is coming out of the page. And when you have little crosses, little X's, it means the current is going into the page. So that means the current in the outer solenoid is like coming out and going in like this. So that means the magnetic field for this bigger outer solenoid is going in this direction. So if that current is decreasing, that means the magnetic flux, the magnetic field is decreasing, and the magnetic flux through that inner coil is decreasing. So it's going to induce an EMF in this inner coil to supplement that decreasing magnetic field. So you would end up, just in our previous problem, you would end up inducing a current in the same direction. So that you would try to supplement that that decrease in the magnetic field. So our current would be going in the coil, it would be in the same direction as the current in the outer solenoid. And remember here, again, it's very important that when we solved for the flux through the inner coil, we plugged in the area of the inner coil, not the area of the outer solenoid, because we just want the flux through that smaller coil there. So be really careful when you're doing these problems that you're plugging in the correct area, since you're almost always going to be looking at coils of different sizes, solenoids of different sizes. So be really careful with that. Okay, so that's this problem. Now we have one more problem to do that's a little bit of a challenge problem. Okay, so this problem is sort of a more challenging induced electric field problem. It's not quite like the capacitor problems that we were looking at. So in this problem, we have a circular region with a uniform magnetic field inside. So this magnetic field extends to some radius r, and it's directed into the page. And we're told that the radius of this region is 8.5 centimeters. So let's just write that. The radius of our region is 0.085 meters. And this region, in this region, the magnetic field is decreasing at a rate of 0.13 Tesla per second. So the magnetic field is decreasing at a rate of increasing, since it's positive. So it's increasing at a rate of 0.13 Tesla per second. All right, so we want to find an expression for the magnitude of the induced electric field at points within this magnetic field. So at some arbitrary radius, small r, inside this region with the changing magnetic field, what is the induced electric field there? So we're going to need this equation for an induced electric field. Remember, this is equal to the EMF, which is equal to the change in flux. And again, we're just looking for the magnitude of the magnetic field, so I'm ignoring all my negative signs. So I'm looking at so since this problem has a high degree of symmetry, I'm going to integrate around a circular path like this, sort of just like Ampere's law, except now I have my electric field. So I'm going to integrate around this circular path here. So my electric field over that path is just going to be E times 2 pi r. It's just going to be the electric field times the circumference of that path. And now this is going to be equal to the change in flux in the area that's enclosed by that path. So the area that's enclosed by this path in here. So this is equal to d dt of the magnetic field times the area. So what's the magnetic field? Well, we don't know, but we know what the change in magnetic field is, right? We know that the change in magnetic field, we were told that dB dt is equal to 0.13 Tesla. So we don't really have to take any derivatives, right? I can just rewrite this as dB dt times the area enclosed by this loop. So let me rewrite this as E times 2 pi r is equal to dB dt. And then my area is just pi r squared, because it's just the area enclosed by this loop of radius little r. So now I can just solve for E. So my electric field, and this is sort of just like how we did in Gauss's law and Ampere's law, I'm just going to divide both sides by 2 pi r. So I get that, I have my pi's cancel, one of my powers of r cancels, and I'm left with just r over 2 is times dB dt. And that is my electric field inside this region with a changing magnetic field. So this is the magnitude of my electric field. And then it says to find the expression for r is equal to 5.2 centimeters. So if you wanted to just plug in r is equal to 5.2 centimeters, you would just plug in 0.052 meters for r divided by 2, and then dB dt we're told is 0.13. So you just multiply those out and you get 3.4 millivolts per meter, or 3.4 times 10 to the negative 3 volts per meter. So the important thing here is to realize that we don't have a wire loop or anything like that here, but we still have a changing electric field. So you don't need to have a wire just to induce a changing electric field. The changing electric field will be induced no matter what if there's a changing magnetic field. So we have a changing magnetic field in some region. This is the equation we want to use. We want to take the integral of the electric field around some closed path, and that will be equal to the change in flux through the area bounded by that closed path. And just like, again, in Gauss's law and Ampere's law, we really only want to do this when there's like a high degree of symmetry, like we have a nice circle here. We wouldn't, this integral and solving a problem like this would be very, very complicated or even impossible if we had some kind of crazy, magnetic field that wasn't highly symmetric like this. All right, so now let's do part B, where it says find an expression for the magnitude of the induced electric field at points outside the magnetic field. So if we're looking, we have a path out here now. So our circular path is now out here. Pretend that's a circle. and our small r is now all the way out here. So that's the radius of our loop. So now what we would do, the same setup. So we have E dot dl is equal to d dt of the magnetic field times the area. So E dot dl is going to be exactly the same. We're going to have E times 2 pi r. And then our dB dt, that's the same thing. It's just that 0.13 Tesla per second. But now our area, we have to be careful. Because now the changing magnetic field is not in the entire area bounded by our loop, right? It's only in this area here where there is a magnetic field. And then all out here, there's no magnetic field out here. So this area all here does not contribute to the flux through this loop, only the area in here. So even though we really want to multiply by the area of the loop for the flux, since the magnetic field is 0 in part of it, we're going to actually only multiply by the area of this circle here, which is pi capital R squared. So we're going to just multiply by pi capital R squared, since that's the region with the non-zero magnetic field. And now we can solve for the electric field. So we have E is equal to, our pi's cancel. We have R squared over 2 little r dB dt. And now that is our electric field once we're outside this region with the changing magnetic field. So once we're outside this area, now our electric field behaves like this. So if we were to plot this, the electric field versus radius, we would see our electric field increases linearly with r while we're inside that changing magnetic field. So it would increase like that. And then when it gets to that outer radius capital R, now it decreases as 1 over r. So then it would decrease sort of like this, where this side is proportional to 1 over r, and this side is proportional to r. So this is definitely, this one that we just completed is definitely a more challenging changing electric field problem. So if you can understand this one, then you're probably pretty set for whatever might be on the final. All right, so I hope that these problems help clarify some things. If you have any questions, feel free to email me. I'll also have office hours on Tuesday before the exam. There's no class on Monday because it's Labor Day, so no discussion, no office hours on Monday. And then Tuesday I'll have office hours. I'll let you guys know. I'm not sure yet when I'll have the office hours on Tuesday, but I'll let you know. And then, and then our final is on Wednesday during lecture time at 9 a.m. to 10:50. And it'll be proctored exactly like the midterm. You'll have an opportunity to upload your work. You'll be able to upload your work for your short answer to get partial credit. And remember to try to write as neatly as you can. That way we can give you as much partial credit as possible. So, all right, so if you have any questions, feel free to email me. Let me know if you have any other questions. Otherwise, that wraps it up for today, and I will see you guys next week.